Hi, and welcome to the Brownbag testing in the utility sector. To kick off this Brownbag, I'll start with an introduction, where I will first introduce myself, give an overview of brightest in the utility sector, and why we organize this Brownbag. My name is Bruno Dubois, and I'm a senior consultant for Brightest. Since 2016, I've been focusing on testing. I've worked for 5.5 years in the utilities, and I'm currently active in healthcare. As you can see, since I've started testing, I had multiple types of roles. Here we see an overview of brightest in the utility sector. During the MIG6 implementation, we had 23 consultants working for 7 customers. Those customers are displayed on the right side of this slide. Currently, we have 12 consultants working for 3 customers: Emeco, Fluvius, and Itineris. This Brownback session is designed to provide you a better understanding of a complex sector, give you an introduction to gain substantial business knowledge, and how we test in the utility sector. The utility sector refers to a category of companies that provide basic amenities such as energy, electricity, water, natural gas, sanitation, and waste disposal companies. In this Brownback, we are going to zoom in on energy, electricity, and natural gas, starting with the energy landscape in Belgium. Here you see a visual representation of the energy landscape. We will discuss how produced/imported energy gets to the consumers. Also, what the responsibilities are for the different actors. Let's start with the producers and importers. They are responsible for the generation/production of energy or the import of natural gas. Electricity is generated in power plants, windmills, water turbines, etc., before it gets injected in the transmission grid. As Belgium doesn't have a natural gas field, we are dependent of our neighbor countries for the import of natural gas. Pipelines are the most common way used to transport natural gas. Beside pipelines, natural gas can be transported under pressure or as a liquid. The liberalization of the market made it possible that producers and importers can compete against each other in order to sell energy to the energy suppliers. Next, we have the energy suppliers. They are responsible for the delivery of energy. The energy is bought from the producers or importers in order to sell it to the consumers. Consumers can be both companies or private, like households, apartments, etc. Only official recognized energy suppliers can supply or sell energy. In other words, they need to be licensed. Since the liberalization of the market, energy suppliers can compete against each other. Energy suppliers are the ones that invoice the customers. Next, we have the transmission grid operators, which are referred to as TGO. The TGOs are responsible for the organization, expansion, and maintenance of our high voltage grids and or the high pressure gas network. They are also responsible for the transmission of energy coming from the producers and importers to the distribution grid operators. Last but not least, they also make sure that our grids are connected between themselves and with the grids of our neighbor countries. 𝗕𝗟𝗂 is a TGO for electricity, while 𝗕𝗵𝐺𝑐𝘄𝗍 is a transmission grid operator for gas. After the TGOs, the DGOs comes into play. DGO stands for Distribution Grid Operator and they are responsible for the maintenance of our distribution grid and the transmission of energy. Public services also falls under the responsibility of the DGOs. Example given, public lighting on municipal roads. The DGOs are validating the meter readings of the consumer and provide them to the energy suppliers. Electricity is transmitted under low or mid tension, while gas is transmitted under low or mid pressure to the consumer. The DGOs in Belgium are Fluvius, 𝗕𝗵ci𝗂𝗂, Oris, and Reza. Official regulatory institutions are responsible to verify if all parties are operating under the standards and rules. They give advice to the government, they do the approval of transmission rates, the calculation of the social tariff, etc. There are federal and regional official regulatory institutions. On a federal level, we have CERG, which stands for Commissie voor de Regulering van de Elektriciteit en het Gas. In the Flemish region, we have VREG, which stands for Vlaamse Reguleringsinstantie voor de Elektriciteit en Gasmarkt. In Brussels, we have Brugel, which stands for Brusselse Regulator voor Energie. In the Walloon region, we have CWAP, which stands for Commission Wallonne pour l'Énergie. The next section will provide a short history. In the previous slides, I've talked about liberalization of the market, free market, and regulations. This section will provide more details about those topics. Before January 2007, we see that production, transmission, distribution, and supply were operating under a monopoly. Since January 2007, production and supply can compete against each other, while transmission and distribution were regulated. For the transmission and distribution, I refer back to the visual representation of the energy landscape. Here we can see that we have a monopoly on a federal level for the TGOs and on a regional level for the DGOs. Liberalization is in that sense not totally correct. It's a combination of liberalization and regulations. The two main reasons behind the liberalization and regulation of the market was to reduce the price of energy by promoting competition and improving the quality of service offered to the consumers. The main goal was to develop a set of rules that did not discriminate between the different actors and respected the rights of the consumers. This all was translated in a set of rules and standards which is known in the sector as 𝗕𝗕. In the next section, I'll explain what 𝗕𝗕 stands for. I'll discuss what the previous standard was, why there was a need for a new standard, and what the current standard is. 𝗕𝗕 stands for Market Implementation Guide, which is a document that contains all the rules on the way all the actors in the energy sector communicate with each other. You can see the 𝗕𝗕 from a business and an IT perspective. From a business perspective, the 𝗕𝗕 describes the end-to-end market processes, while from an IT perspective, it's a description of the exchange messages that support the market processes. The previous standard was the 𝗕𝗕4. Here you see an overview on how the market communicated. On the left side, we see the DGOs. They all had their own clearinghouse to communicate with the market through the web portal 𝗲𝗏. On the right side, we see the five biggest suppliers: Eneco, Luminus, Essent, Engie, and Lampiris. What's important to remember on this slide is the fact that each DGO has its own clearinghouse. You might wonder why there was a need for a new standard. Simply said, as the market evolves with new technologies or services, such as digital meters, local production, electronic vehicles, smart houses, etc., the market processes needed to be adapted. Next to that, it will provide more flexibility for the consumers, which made it more customer central. This all translated in the current standard, the MiG 6. The big difference with the MiG 4 is that the DGO doesn't have their own clearinghouse anymore. It's replaced by a centralized clearinghouse, which is a neutral platform who handles the message exchange between the DGOs and the energy suppliers. That centralized clearinghouse is called CMS. CMS stands for Central Market System and is a central IT platform that facilitates the exchange and processing of the information between all the actors in the Belgium energy market that is compliant with the MiG 6 standard. The responsible for CMS is 𝗕𝗄𝗄𝗏. 𝗕𝗄𝗄𝗏 is a joint initiative of the DGOs in Belgium. The company was established on the 9th of May 2011. CMS came due to the integration of the evolutions of the market processes and results in a less error-prone, cost-efficient, customer-central functioning of the energy market. After postponing the go-live date a few times, eventually MiG 6 went live for the DGOs in November 2021 and for the suppliers in December 2021. The following slide will show the high-level differences between the previous and the current standard. The first point we already discussed in the previous slides. Regarding the market transaction, we went from 39 scenarios to 14 modules. The switch unit went from 𝗂𝗏 to SDP. The grid fee calculation was done in the backend of each DGO, and it's now done in CMS. We went from batch to transactional processing. Smart meters and local prediction were added in the MiG 6. And the allocation calculation was done with synthetic load profile and it's now done with real load profiles. As explained in the previous slide, the EIN was used in MiG 4, which referred to head point. The head point is an identifier for the technical installation. For each contract, a point of delivery can be linked to the head point. In MiG 6, we worked with SDP, which stands for Service Delivery Point, which is a unique value between the grid and the market. In fact, it's a combination of the EIN with the service component. Due to the introduction of a service component, it is possible to have multiple contracts on one endpoint. Here we see an overview of all the services in MiG 6, from pure consumption to pure production and all the possibilities in between. As you can see, there is also the possibility to have two suppliers. In short, MiG 6 made it possible to take or inject energy from the grid. In the next section, we'll zoom in into the market processes. To be more precise, we'll zoom in into the market processes from a business perspective. In this overview, you can see on the left side that market processes can be triggered by the DGOs, the suppliers, and the consumers. The market processes that are triggered are divided into several domains: structure, measure, settlement, billing, and rectification. In this slide, you can see how all the domains are connected to each other And in the following slides, I'll explain what each domain does. The first domain is structuring. The structure domain contains all the possibilities for actors in the utility sector to create, modify, or end the contract with the consumer. An example of one of the possibilities is the registration of a contract. A consumer signs a contract with an energy supplier. Then CMS verifies if that demand can be sent or accepted. When the demand is accepted, the DGO is notified that there is a new contract and that the meter can be installed. If there is already a meter installed, it can simply be activated. The structure domain contains a lot of triggers to initiate a process or processes. For example, a customer can move in, or a customer can install solar panels, and as a result, the 𝗕𝗹P trigger is launched. A customer can move out, or a customer can, for example, switch from supplier, and as a result, the 𝗕𝗓C trigger is launched. The business master data can be updated, or the customer metering configuration can be adapted, for example, when an installed meter switches from total hour to high-low. The next domain is measure. The main goal of measure is the sending out on time of the received, calculated, and validated indexes and consumptions. Measure is the basis for other domains, such as billing, rectification, and settlement. Meter reading can be done either manually or automatically. MMR, or manual meter reading, is either done yearly for small or normal volumes, or monthly for big volumes. AMR, or automatic meter reading, is done for electricity every 15 minutes, for gas every 60 minutes. Classic AMR reading is done once a day. For GOL, gas online, it is done hourly, and for infeeds, it's done in real time. This is all billing relevant measurement data. Next to those presented on the slide, we can fetch meter readings in function of a certain process, for example, switching of a meter, or on demand of the customer, or as an initiative of the DGO. The next domain is billing. Simply said, billing is the calculation of invoices. In order to do that, we need tariffs. A couple of examples of what the tariffs are distinguished on is grid fee versus PSO versus TRC, the fee versus the reference advance, if it is gas or electricity, the service component that's used, or the start and end date. Tariffs are necessary for the calculations, otherwise we don't have a valid tariff. Very high level, billing works in 3 steps. The first step is the calculation of grid fee by the DGO in CMS. Then the suppliers pays grid fee to the DGO based on the grid fee billing frequency. And in the last step, the supplier invoices the grid fee to the consumer based on the energy billing frequency. The next domain is settlement. The main goal of settlement is the pursuit of a fair distribution of the volume, both estimated and actually recorded volumes, between the various players in the energy market. This falls under the responsibility of the DGOs. Settlement contains four processes: pre-allocation, allocation, reconciliation, and reconciliation of compensation. The calculation can be done on the service delivery point or via the time of use. In-feed is part of the settlement domain. In-feed is a defining and controlling of the energy flows within the DGO grid. Simply said, it's the netto energy injections versus the outflow in the DGO grids. This is measured by AMR meters. And the last domain is rectification. Rectification describes the processes used by the various players in the market to gather errors in the collected data in order to report, follow up, and correct them. An example of rectification can be a spontaneous correction by a DGO, where an index is recorded, but we notice that the previous index was wrongly estimated. Then rectification is triggered based on the recorded index. And as a result, the corrected data is sent to CMS and the market. A few examples of what data can be corrected. We can correct relational master data. We can correct technical master data. We can correct meter readings or invoices. Rectification can be very complex. There are a lot of dependencies between the already sent out data that has been sent out on different time points and through different messages. Multiple parties can also be impacted by those corrections. Before I go over to the next section, I'd like to mention that this is a very high-level overview of all domains. For those who are interested in more details per domain, we have created an energy course that covers that. The next short section covers message exchange. In other words, how the MIG is described from an IT perspective. The language that is used is XML. XML is a software and hardware independent tool for storing and transporting data. It stands for Extensible Markup Language, and it is a W3C recommendation. The XML can be validated against an XSD. An XML schema describes the structure of an XML document and is also referred to as an XML schema definition. It contains the elements and attributes that can appear in a document, the number of and the order of the child elements, the data types for the elements and attributes, and the default and fixed value for elements and attributes. XSD is used as a first validation to check if the sent or received XML is compliant with the defined XSD for that type of message. Here we can see an example of a measure XML, specifically for a start index. All the messages that are exchanged have a unique name based on the type of message or information that is sent. A couple of examples for measures are the 𝗵𝗶50 for time series, the 𝗵𝗶60 for volumes, the 𝗵𝗶70 for the start index, and for in-feed, the 𝗵𝗶110. When we look at the XML, we notify that it specifies that it contains the information for a start index. In this case, the meter has two registers, one for high and one for low. and they both have a start index of 10. For the last slide of this section, we can see a high-level example of the message exchange. This is an example where CMS requests an index. In the first step, CMS requests the index to the backend of a DGO. The DGO will send the index to CMS. CMS will send that index to the backend of the supplier. And CMS will confirm to the DGO that the index has been sent. In the final section, we'll discuss testing. Here you can find an overview of all the test phases from a CMS point of view. All the market parties need to follow those test phases as well. This is regulated and should be executed in sequence. The later the test phase, the more parties that are involved. The first test phase is FAT, which stands for Factory Acceptance Test. This is the first test phase when a scope item has been developed. Also, defect fixes found in later test phases will always be tested first in FAT. Next are the site acceptance tests. This phase can start when everything is successfully tested in FAT. Those test cases are executed by SAT ATRAS testers through third parties. In the next phase, DIT, which stands for DGO integration test, the DGOs comes into play. In this phase, the integration with the DGO backends is tested by DGO testers. After DIT, the suppliers comes into play for the market integration tests. In this phase, the integration with the supplier backends is tested by energy suppliers. Before the go live, the final test phase was transition. During this phase, we validate if all parties can handle the transition of MIG4 data to the MIG6 system. The main test and defect management tool is 𝗵𝗵. Due to regulations, CMS is obliged to use this tool. Other market parties can use a different tool. ORES works with 𝗵𝗵 as well. Therefore, I gathered some tips and tricks based on my experiences from a test and defect coordinator perspective. Basic analysis can be done in 𝗵𝗂𝐶, for example, creating simple graphs. One that I used a lot is the creation of favorites. You can create personal favorites that I use to follow up specific topics such as defect retests. Or you can create shared favorites that I use to create an overview of all the open defects per domain. You can also organize views. In the example of the overview of all the open defects per domain, you can group them as well per severity or by status. When a release date is postponed, for example, you can use the mass update functionality to update all the target dates of all those defects in that release. Duplication and linking of defects can be used, for example, when a blocking defect is found and we can deliver a workaround. In that case, the original defect can be duplicated for the workaround and can be linked to the original defect. Also, defects within a specific domain that are related to each other can be linked. For advanced analysis, you can extract the data out of 𝗵𝗂𝐶 either in the front end or by using SQL. To finalize this presentation, I'll share some tips and tricks divided into categories. The first one of the general is acknowledge the complexity of the sector. Throughout the presentation, we went over the different actors, the different domains, the different types of messages, and so much more. A small change can trigger a lot of changes in a domain and even in other domains. Therefore, become an expert in your domain and gain cross domain knowledge. One of the most important ones, communication is key. Within the test team, within the IT team, between IT and business, within the organization, and within the market. For testing, it's important to have a clear defined release scope that is aligned internally and externally, especially when there are dependencies between the different actors for the same scope item. Create the test design in function of the test phase, meaning in FAT you will focus more on the functionality, which will be tested by mocking of the messages, while in mid the focus will be more on the integration with all the parties. Prioritize in function of the impact of the market. When I was coordinating the FAT test cases, we used P1 where there was a high impact on the market, P2 when there was a medium impact on the market, and P3 when there was a low or no impact of the market. I think the last two are known by everyone, meaning documentation, 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 and involve testing as soon as possible in the software development lifecycle. For regression, I'd like to advise to organize your regression set by domain, and per domain, organize them per functionality. If possible, depending on the test phase, automate the regression test cases. For defects, it's important to have a clear definition of the severity of the defects, both internally and externally. It's important to speak the same language when we classify a defect as a blocking defect, for example. Link the related defects. The remaining tips and tricks are similar to the ones presented in testing. Prioritize in function of the impact and need requests of the market based on the severity. Have a clear defined release scope that is aligned internally and externally. And the last one, documentation, documentation, documentation. This is the end of the presentation. Thank you all for participating. We'll now go over to the Q&A section.